Right, we're starting the next chapter, chapter 6, hypothesis testing with discrete variables. We've already done it with continuous variables, so some of the concepts we've used then we'll just keep going with this. So I'm just going to go straight into an example and we'll discuss what you might want to do and we'll see whether or not you've got the right ideas. So I'm not going to write it out in full, but basically we have some medicine which historically cures 2/5 of people who use it. So we have some medicine, historically it cures 2/5 of the users. Now a new drug has come along and there's a claim that it's better. The claim is it's better. There's been a clinical trial, and in the trial it cured 11 out of 20 people. And what our job is to test at the 5% significance level whether or not the new drug is better than the old one. If you think about it, this is quite a common real-world example. There's millions of pounds in the drugs industry, and that's not the illegal sort, that's the medical sort. Yes, there is billions probably in both actually. So this sort of thing is very important. I mean, there are clinical trials, all sorts of things. When I was at university, one of the options I did in my degree was in medical statistics, and that's a huge area of sort of testing things. Is it worth it? The government want value for money. You see in the papers and in the news sometimes that NICE, which is the National Institute for Clinical Excellence, now decide that the NHS can use this drug, can't use that drug, and all sorts of things. And a lot of it is done on medical testing and things like this. So here we go. Let's just look at the scenario. We've got here 20 patients, 11 of them cured. Any distributions we have dealt with so far, would they fit this scenario? Because we need to think about our distribution first of all.
Would it be binomial?
Binomial is correct. So can you tell me why you thought it was the binomial?
You had the number of successes in the number of trials.
Yeah, okay. First of all, here we had a fixed number of trials, which in the binomial we call n, and that was here 20. We tried it on 20 people. And then what we have done here is we have counted the number of successes, which we usually call R, and that was found to be 11. What other letter, what other parameter did we use in the binomial distribution other than N and R? P. So P was the probability of success. Well, all we had to go on initially was it's supposed to be 2/5. So probability of success historically is equal to 2/5. So yeah, it is the binomial distribution, so well spotted, Lewis. Okay.
Why is the probability of success 2/5 when it's a different drug?
Well, historically it was. So what we've got to see is, has that changed or not?
Isn't that good?
So, I mean, let's go straight on to our two hypotheses. H0, the null hypothesis, is going to be, as I think we said when we started the last chapter, basically the status quo. Nothing has changed. So we will say that P is still 2/5, that the new drug is not any better. And I would, P equals 2/5, I ought to have said here for new drug. P equals 2/5 for new drug, i.e. the new drug is not any better than the old drug.
Would it not be P is less than or equal to 2/5?
Well, we just say no change, so no change at all. The H0 has always got an equals in it.
Okay.
H1 won't. H1 is that P is now greater than 2/5 for the new drug, i.e. the new drug is better. Than the old drug. So if we've changed our problem into that, what do we usually write down at this stage? Yeah, whether it's a one or a two-tailed test, and because that's a greater than sign in there, this then will be a one-tailed test. Just like last time, there are a couple of methods you can carry out these tests. We're going to do the easy one first. We'll just write down here again that we had a significance level of 5%. So that's just formulating our question, effectively. Now what we're going to do is to work out a way of coming to a conclusion. Are we going to accept or reject H0 or H1? So this is our method that we are going to use. We are going to find the probability of getting our observed result or better than that under the conditions of H0. And then if the so what we're saying there is going to find the probability that we actually would get 11 or better than 11 results if P really is 2/5, because that's what it states in H0. And then if that probability is less than our significance level, so if the probability of getting what we have seen is smaller than 5%, we're going to say, hang on, it's so unlikely to have happened, we don't believe it is 2/5 anymore. We will reject H0 and we will accept H1. So if our probability is small, we will reject H0 and therefore accept H1. However, if the probability is greater than or equal to our significance level, we will just accept H0, saying, well, there's quite a high chance that could have happened anyway under the old drug, so no evidence of any change. So that's the methodology we'll use, and at this point I'll just stop this video clip and I'll start another one. So what we've got to work out then is the probability of getting our observed result, which was 11, or better than that, so 11 or more. We want the probability of getting 11 or more. Now, if I'm writing this down, I really ought to have stated somewhere already what X actually is. So X is the number of patients cured. And I also need to state what distribution I'm using. Well, we talked about it earlier. We said X then will follow the binomial distribution. We said earlier N is 20. And under the conditions of the null hypothesis, which is what we use, P is 2/5. Right, how would you go about working out the probability X is greater than or equal to 11 from the binomial distribution here? 1 minus the probability that X is smaller than 11. Yes, smaller than 11 is true. The tables always have less than or equal to, so 10, which is exactly what you said. Less than 11 is the same as less than or equal to 10. So reach for your tables. Do your tables have N is 20 in them? If you do, tables do have N is 20 in them for binomial. Do they have P is 2/5 in them? Well, I've chopped the corner off my tables. Oh, and I do, no, it does have 20. I reckon it's on page 13. N is 20 is page 13. And 2/5 is 0.4. That's there. And I can read off a probability for 10 of being 0.8725. So I would do 1 minus that. So I just got that straight from my tables.
So what's the formula?
Yes, there's one on the table up here. Okay. Can I go back there, because it might be there for a reason, it's not in my room. So I have this here. Well, that's 12.75%, that decimal. So if we go back to what's at the very top of the board, is that probability less than 5% or greater than or equal to 5%? Greater than or equal to 5%. So I'm going to accept H0. It's not such a rare event. If the old medicine would have come up with that number of people, or better than that number of people cured, 12%, 13% at the time anyway. So there's no actual evidence that the new medicine is any better. So we can say then, at the 5% significance level, there is no evidence which will lead us to reject, no evidence to reject H0. So we therefore have to accept H0, and H0 then was the new drug is no better.
In reality, would you then do the test again and again to see if it's consistently getting?
I mean, yes, you could do. I mean, you could obviously the larger sample. Yes, the larger sample size, the better. And it depends on what sort of drug and what sort of illness as well.
Yes.
I mean, sometimes if it's a very rare condition, actually doing on 20 people might be quite big, because it's tricky. If it's a cure for the common cold, well, you should be able to do it a lot more. And if each pill costs £20,000 because it's brand new, I mean, you're only going to do that on 20 patients if you really think you're going to make a decent profit afterwards. It's all sorts of things sort of will come into here in real life.
Why
That
do
was
you
great,
accept
then.
H0?
We accept H0 because of what we wrote down here. We only accept H1 if this probability here is smaller than the significance level that we are using. Because it's only if that probability here is smaller than that, we say, well, the chances of it happening through the old drug is very, very small. Okay, just going to stop recording at this point. So, just like there are two methods of doing this with continuous, there are two methods of doing this with discrete as well. And you might already have asked yourself from that last question, well, how many out of 20, they cured 11 out of 20 last time, how many out of 20 would it have to have been that we did accept that the new drug is better? And that comes really from looking at it from the critical value approach. So what we're going to have now, well, let C be the critical value. So in this example that we've just seen, that would have been, well, how many patients would they have had to have cured out of the 20? That's what that C would be. To assume that, or to accept that the new drug actually was better. Well, we want then the probability that we would have observed this critical value, or even more people cured than that, going back to what Tom asked a minute ago off camera. We want the probability of getting that to be less than, I'll put in or equals to, it doesn't really matter, I suppose, our significance level. So we're trying to find now a critical value such that seeing that many people cured, or more than that, would have had a less than 5% chance under the conditions of H0, null hypothesis. This is a greater than, though. We don't like greater than. We need to change it round into a less than or equal to. What is the opposite of greater than or equal to C if I'm going to write down a less than or equal to inequality here?
Do you have to put 1 minus P and then C minus 1?
You say that last bit again?
C minus 1?
Yes. Okay. The opposite of greater than or equal to 95 is less than or equal to 94. So this C minus 1 here is really important. And I'm turning that around. What will this number over here be then? So I'm turning all of this around the other way around. Yes, 0.95. Okay. And I'm turning it round because our tables are less than or equal to tables. And this fact here, that this now is C minus 1, that is quite important, that you actually remember to do that. So what we want to do now is we want to go to our tables, and we are going to use the n is 20, the p is 2/5, which is 0.4 as a decimal. And what we are trying to find is the first probability in our column which is bigger than 0.95, greater than, well, probability greater than 0.95. So look at your n is 20, p is 0.4, go down that column, find the first number that is bigger than 0.95. What is that probability, and what is the x value that goes with it? 0.9790, yes, and the x value that went with it is 12. Right. So that 12 pairs up with that c minus 1. So our c minus 1 is 12, which means that c is 13 or better. So that means in the trial, if they were going to trial it with 20 patients, to conclude that the new drug was better, we would have wanted to see 13 or more people cured. So that 13 there is our critical value. And we would make our decisions that if 13 or more out of the 20 people had been cured, we would have rejected H0, which means we would therefore have accepted H1. And to be honest, whilst the first method is easier, I think if somebody was asking you, if the drug manufacturer was asking you to do this, they would be more interested in this. So they would want to know, oh, we were 2 people off, were we? You know, how close were we? We were 2 people off.
How can we change the results?
How can we fiddle the figures? No, not how we can fiddle the figures. No, we need to make our pill better. Okay? So, that's the alternative approach of finding the critical value, which gives you more useful information than just replying back to the chemists, no evidence. It actually gives them and how far off were you?
Wouldn't it be better to have a smaller sample? There would be less people on.
Well, as we said earlier, the bigger the sample, the more reliable your results.
But they want to be closer.
Yes, but you still want a bigger sample. The bigger the sample, the more reliable your results anyway. So I'm going to pause the video there and we're going to move on to a different example. So this is the second example, the second scenario we're looking at. We've got a memory test with 10 objects. So maybe you're shown 10 objects on a tray. I think this used to happen on the Generation game. Remember the conveyor belt on the Generation game? Or was that just before your time? And you had to remember what was on there. And you had to say, cuddly toy, there's always a cuddly toy on it. And there are things like fondue sets, which in the 1970s were just amazing, and tea makers and things like that.
And that's spinning the wheels.
I think spinning the wheel's a different one. But anyway, it might have been. I have to say, my knowledge of the Generation game isn't complete and brilliant. Not at the moment. Example number 2. Memory test. 10 objects are shown to you for a period of time, then maybe they're hidden or removed, and you've got to say how many of them you can remember. Now, historically, okay, when people have been doing this, there has been a success rate which averages at 35%. So that means, on average, people manage to get 35% of the objects remembered.
I thought 35% of people remember the tag.
No, okay, that says basically on average people remember 35% of the objects. Okay? Now, what is happening now is there's this new energy drink called Red Cow on the market, which is supposed to boost people's mental performance. Okay? And people are now given this drink or whatever it is, and then they are asked to do this test. So they do the test.
Will it be the same objects?
It would be, yes, everything in the test is the same. The test is the same. So the question I'm asking you is this. What would the success rate have to be to show evidence.
Does it say best or test?
Test, it should say. What should the success rate have to be to show... where are you asking about, Billy? Here.
Energy drink, best or test?
That's supposed to say test there.
Okay.
Sorry. They're having energy, then they're taking the test. Energy drink, then they're taking the test. What would the success rate have to be to show evidence that the energy drink improved people's results? Improved performance, shall we say.
Do we still need to do H0 and H1?
Yes, we will still have to do all that sort of stuff. Okay. So, again, the first thing I think I asked last time when we looked at this was, I said, does this look as if it is any distribution we have come across so far? Now, the fact that we are doing at the moment discrete hypothesis testing means, well, you only know about two, the binomial and the Poisson. But remember, in the exam, it won't be labelled up, by the way, this is testing you in discrete hypothesis testing. But you need to realise that, you know, this is a discrete one. So is it binomial or is it Poisson?
Is it right?
It is binomial here that we're looking at. A fixed number of trials. So, again, here we have fixed number of trials. We have that under the null hypothesis, historically, there's a constant success rate. So, historically, constant success rate, that's telling us that P is 0.35. The fixed number of trials, that's telling us that the N is 10. And what we're after here, what we want to know is what our critical value is. And you can think of that really as our R value that we are after, if we are going binomial. So we'll say X is the number of items remembered, and the X at the moment is binomial 10, 0.35.
What is the significance level?
We'll use 5%. Okay? So, we'll use 5%. We weren't told, so we'll use 5% significance level.
Should you always be doing that?
They'll say in the exam.
Oh.
But it's a generally used one. Most scenarios use 5%. Mind you, if I was spending lots of money, I would want a much smaller level there before I invested lots of money, because it'd be a 5% chance that it was all a fluke. I wouldn't want to invest lots of money if there's a 5% chance that it could all have been a fluke and my pill's rubbish. What we are going to look at in the next chapter is looking at what happens when you change the significance levels, what risks and what benefits does that have. So that comes in the final chapter. Okay, so H0 here is to do with P. H0, historically, P is 0.35. What we want to know now for H1 is... yeah, okay. My notes here I wrote it down differently. Is it just changed? But no, we'll go for improved performance. So then P is greater than 0.35. Actually, can we change it to P not equal 0.35? Yeah. And can we go back and change up here to has the energy drink changed performance? Because we haven't done a two-tail one yet, and I would like to do a two-tail one. So we'll change that up there if you don't mind. Has the energy drink changed the performance? So we do have experience of doing a two-tailed test.
It could make you really stupid, that energy drink.
It could make you really stupid, yeah. You don't really want to market your drink. Have this new drink called Red Cow. It makes you really stupid. Imagine that as a strap line. Who would go and buy it? Really stupid people, I guess. Right, okay, so what we've got here is a two-tailed test. Now, I'm going to draw a graph, effectively now, of what we have got here. We've got here X, and up here we've got probabilities. And what we are going to have here is probability bars. Whether I can get... how many? I need 11 bars here altogether, wouldn't I? I just might have a sort of dot somewhere. I don't know exactly what shape they are. I'm going to put a sort of dot there. But I could have from 0 to 10. Okay? So I've got sort of bars like that. Now, if it's a two-tail test at 5% significance level, now I don't know where these lines, I'm just going to draw lines on here, I don't know where they actually will be, I haven't done that yet. But what I'm looking at is, there'll be a line here, and it might go through a bar, it probably will go through a bar, and a line here, where over here, there's 2.5%, and over here, there is 2.5%. Now, before we actually go ahead and do anything, this next bit is quite important. Let's assume I've got my lines in exactly the right place, going through the 9 bar and going through the 0 bar.
That's the 1 bar.
Sorry, the 1 bar, thank you. What would be my critical values to tell me that my drink has had an impact? How many, remembering how many items? Here, the 1 bar, some of the probability in the 1 bar is not in the critical area. So if somebody scored 1, for example, you don't know actually that is one of these very small results in the tail or not, because they could have come from that part of the 1 bar to the right of the line, which isn't in the tail. So actually, if my line is in the right place here, we would reject H0 for a 0, but not for a 1. Because if it's a 1, we don't know whether it's come from the left-hand side of the line or the right-hand side of the line. And over here, likewise, if we got a 9, because some of the probability for the 9 is not in the tail, only some of it is, we couldn't actually accept, we couldn't say that we would reject H0 if we got 9. We would only have to do it if we got 10. That becomes important later on. But I don't know. Those green lines were just drawn in sort of random place at the moment just to demonstrate a point. What we're going to do now is do the calculations and see what we actually get.
So if you drew a line and found it was going through, like, most of 1 was outside, but only a tiny bit was in, sort of the 1 with 1.
You still have to reject it,
right.
but you still have to not use it. I won't use the word reject. Not use it in your critical region, because the result you got could be the bit that is not in the critical region. You still say no, can't conclude. So,
what if it was in 0 and 10?
If it was in 0 and 10, then you probably need to have more. Yeah, well, or just do it more times to get something like that. Okay, right. So here we go. This critical region over here, we are trying to find 2 critical. If I label that one there, and it's C1, critical value 1, and that there, critical value 2, we want to find the probability that X is less than C1 has to be smaller than 2.5%. And we have to find the probability that X is greater than C2 to be also less than 2.5%. So in the scenario we're doing now, we are going to use binomial tables. Now you may be able to do this on a calculator by doing an inverse one on a calculator. I'll leave that up to you to find out whether you can do that easily. Binomial tables, here we're dealing with n is 10, p is 0.35. Now I've got a note here that in the S2 books, if you're using tables from the S2 books, they've printed the 0.35 and the 1/3 columns the wrong way round in the textbooks. In the textbooks, apparently on page 162, they have printed 2 columns the wrong way round. In the formula book, you're okay. So if you're using a formula book, and I've got here formula book should be page 11, then we should be okay. So, I reckon we are looking for X values and probability. Well, what are we finding? What
So is that
is
1/3 and 0.25 for the whole table?
well, no, and just in that one, just on page 162, I think, of the textbook I've got a note. And if you look at it, the numbers you can see, because the numbers, instead of following a pattern as you go along, there's a little peak in it. But if you use the green formula books, they're fine, they're accurate. So what we are looking for, first of all, is the biggest probability we can find, which is greater than 0.9 0.025. So what you're looking for is the biggest probability that's less than 0.025. What's the biggest probability you can find that is less than 0.025? Smaller than 0.025 in that column.
0.0135.
I'm agreeing with what Chelsea said. 0.0135, which belongs to an x value of 0. Okay. Then what you're looking for, the second time, is you're looking for the smallest probability, which is greater than 0.975, which is up at the other end, which is corresponding to this one here. So you're looking for the smallest probability that's bigger than 0.975. What is that?
1.
Not what I've got down here. 0.9952, yeah, which corresponds to an x value of
7.
7. Yes. Okay. So, well, I'm going to do a little sketch here again of the sort of graph. What I've got here is I know that the 0 bar, I know that the probability, I'm going to put a 1 bar in here as well. I know that the 0 bar, if I put a line in here, to the left of that, I know that that is 0.0135. And I know that the 0.025 is somewhere here in this bar, because the one number is more than that, because that's included all of that. So the 0 is critical region. The 1 is not. And then if I put sort of my dot, dot, dot up here, I've got a 7 bar, an 8 bar, a 9 bar and a 10 bar. You've just told me that the probability of being less than or equal to 7 here, being left of there, is 0.9952. What does that tell you about being right of there? If you take that away from 1, what does that tell you about being right of there? Okay, so sorry, that line would have been somewhere in the 7. Sorry, I ought to put that line somewhere in through the 7. Sorry, somewhere through the 7, not after the 7. Sorry.
I can know somewhere through the 7.
Because if it had been exactly at the end of 7, you would have found in the tables 0.975. You didn't find 0.975 exactly in the table. You looked for this number here, which was the number, which was the smallest number bigger than it. The important thing is that this here, these values here, are your critical region. It's like coming back to when we had that last example, particularly the upper end, that 7 is like your C minus 1. If you go back to the last example we had here, the big end, where the numbers are big, that is like your C minus 1. And here we had to add 1 on to get where our critical region started.
Yeah.
You have to do the same thing here. That table gave you 7. At the big end, where the numbers are big, you have to add 1 on, so the critical region here will be after the 7, because some of that 7 is in it and some of the 7 is not in it. So the critical region is 8 up at that end. So what we are going to get here are the critical values are 0, 8, 9 and 10. So only if people were remembering 0 items or 8, 9 or 10 items after the drink would we be accepting that the drink had made a difference. I'm going to stop the video there. So this is the second lesson we got on hypothesis testing with discrete variables, what we started last time. Example 3 is all about a drawing pin, or several drawing pins. And we know that the probability of a drawing pin landing point up from lots of trials in the past is 0.35. What happens now is that 400 trials take place, and in those 400 trials 150 times it lands point up.
You put
153 times is correct. Sorry, I said the wrong thing, I think. 153 out of those 400 times it lands point up. So what we are testing here is, I think these may be a new batch of drawing pins, these 400. So what we're doing here is we're testing at the 5% significance level whether or not the probability of landing point up has changed and is now greater than 0.35. So that's our scenario. Historically it's been 0.35, new batch of drawing pins has come in, 400 of them have been thrown on the floor, 153 of them, they came point up. We want to know basically whether the point up probability has changed or not. So, first of all, what distribution are we dealing with?
It's changed or got greater?
It's greater.
Okay.
Greater. What did I say changed? Made greater. Okay, what distribution is this reminding you of?
Binomial.
Binomial. Okay, so x is going to follow the binomial distribution, where x will be the number of point-up pins. So x here will be binomial. What will my two parameters be? 400, that will be my n, and my historical p, 0.35. Okay, and that is the p there that always comes from your null hypothesis, which is basically your old data. So I ought to then write down what my h naught is. My h naught is that nothing has changed. P is still 0.35. We were told in the question the alternative hypothesis is p is greater than 0.35. Then the methodology we were using from last lesson was we were trying to find what's the probability of getting what we saw, or even more extreme of that. So what we have to do to work out what we're going to do is find the probability of 153 or more point-ups under the conditions of h naught. So what I want then is a probability that x is greater than or equal to 153, and I will use my binomial distribution 400 0.35 for this calculation. Right, any comments? Yes, that's right, okay? Because this is so big, you will need to use a normal approximation. Okay. So, the normal approximation, if you're going from BNP...
Would we lose marks for doing it normally? Because I can just use a calculator.
Your calculator will just do that now, will it? In that
no, lose marks if we do a binomial.
No, will your calculator deal with that binomial probability with those numbers?
So,
Yeah.
Yes.
Okay, then unless it's said in the question using a suitable approximation, no, you wouldn't. In the old days, it just wasn't practically possible to do that. So, binomial NP, what does that change to for the normal distribution?
NP and then NPQ.
Yeah, NP and then NPQ, where Q is 1 minus P. So here then, we're now going to be saying, just going to move this up a bit, that X is now normally distributed N times by P, N times by P times by Q, and that is 140.91 apparently. So I want the probability that X is greater than or equal to 153. Any comments? Yes, you do have to use a continuity correction, that's right. Because we were going from something that was discrete to something that's continuous. That was true for the binomial distribution, but I now need to use a normal thing here, so I need to change this. I need to use from there to there the continuity correction. So I wanted 153 or more. What will I change that to be for the normal distribution? Is correct, because that would include 153, and it was strictly including 153 there. So that's correct. Okay, where would we go? Where would we go from here? Yeah, that's right. Flip it around to a less than. We don't like greater thans. So it's 1 minus the probability that x is less than 152.5.
If you already break that or equals on the normal...
That would make no difference due to the Billy principle. Yes?
If you were to use your calculator and just change it once into binomial,
Yep.
you get 1 minus the probability, but then it's changed to greater than to less than, right?
Yes.
When you're doing the binomial, what changes again? Well, because it changes instead of being 153, so you're at 152.
If you did it on the calculator using the binomial, you would stick with 153. Because you're not going to you're not approximating it by a continuous distribution, so you just keep it in there. It'll be interesting in a minute to see what your answer is for the binomial compared with the normal approximation. Right, we've got 4 or 5 minutes left, so if I tell you now, that works out to be, here's the phi calculation, 152.5 minus 140 over root 91. That comes out to be 1 minus phi of, if any of you have done it, 1.310. 1 minus 0.9049 comes out to be 0.0951, which is about 9.5%. I don't know what you got if you did it on the binomial from your calculator. Calculator binomial. What did that give you if you did it on a calculator? Anybody managed to do that? Didn't in the end. Has anybody done it?
I got, I think, about the same thing. Yeah.
About the same thing.
I'm doing that.
I'll leave that up to you.
So what would you use?
Right, well, let's have a look. So what we've said here, the probability of getting what we've seen, well, there's a 9.5% probability that we would have got that by chance. So, as that probability is not less than 5%, we will accept H0. It could have just happened by chance with a 9.5% chance, so we'll accept H0. So we will conclude that, it's not mu here, is it? It's P remains at 0.35. There's nothing to change our minds on that.
I've got 0.0956.
You got
956.
Okay, so you're out by one figure in 2 significant figures, aren't you?
Yeah.
So yeah, that's very close. Okay, put that in there, thank you. So that's what you would have got as a binomial. So, there we go. We've got one more example to go, which I think we'll probably save for next lesson now, because we've only got about 2 minutes left. This is the final example now on hypothesis testing with discrete distributions, and we are dealing this time with accidents that occur at an average of 6 accidents a month. We've called this again road accidents that happen somewhere. The council weren't very happy, so the council put up new signs. And then, after the signs went up, in the next month, there were 3 accidents. What we are trying to establish is, have the new signs lowered the rate of accidents, lowered the accident rate? So that is a summary of the question. We'll worry about that in a minute. Okay? So accidents occurring at an average rate of 6 a month historically. New signs are put up. In the next month, 3 accidents occur. is there any evidence that the new science have lowered the accident rate? The very first line up there, what is the very first line suggesting to you? Poisson, yes. The average rate should be suggesting that we are using the Poisson. So let's define a variable. X is going to be the number of accidents a month, and we will say that X is going to be Poisson at 6 a month. That's under the null hypothesis. So our null hypothesis is going to be that, lambda is 6. Our alternative hypothesis is that, well, so new science had lowered the accident rate. So what will a less than 6? Okay, so we're doing a one-tailed test. So what will we do what calculations do we need to do to decide whether or not these have made a difference? Well, we will have to decide in a minute on something, but I don't want to go down the level of significance first of all. I'm just saying, first of all, what calculation will we actually be doing here? Yeah?
We want to turn it into the normal distribution. Is that what we want to do?
Is there a need to? Not if lambda's that small. There's no need to. You could, if lambda was big and met the criteria, you could do it. What would you have to remember in doing that? Yes, that's right. If you went from Poisson to normal, you'd have to remember the continuity correction, yeah. We don't have to do it here. But what calculation are we going to do? What's our test statistic, if you like? What are we going to do? Think back to how we were doing these last time.
Probability of 6 a month. 3 happening under the original conditions.
Nearly perfectly right. You've just said find the probability of 3 happening in a month under the conditions of H0. Nearly right. Just need to maybe put a few extra. Yeah, 3 or less than. 3 or basically more extreme than that. So 3 or less than, yeah. So what we need, the statistic that we need is we need the probability that X is 3 or more extreme than 3, which here is lower than 3. So that is what we want.
What is the significance then?
We haven't actually said that yet. Rob's asked for it 3 times and I've refused to give it to him so far. Okay, so we'll see what probability we're going to get here, and it may just be blindingly obvious. I mean, if it comes out as being 0.000001, well, who cares what the significance level is? I mean, we're going to reject H0 anyway, aren't we? So you need to do this. It's either tables or it's writing out formally and adding up, or if you know what you're doing on your calculator, just going to your calculator.
It's quicker to calculate.
Okay, so we've just heard it's quicker to use the tables than a calculator. I agree. Poisson 6, less than or equal to 3. I reckon you can just read that number off. Okay, Poisson 6, less than or equal to 3, 0.1512. Great. So we do need a significance level, okay? Generally, no, Rob, yeah, you're right, Greg, yeah. If we say we were going to use the 5% significance level, say that we'll use a 5% significance level, what would we conclude here?
It's greater than 5%, so we accept H0.
Yeah, we have here our probability is greater than our significance level, so we would accept H0. So in other words, we've said there's a 15% chance. Yeah, sorry. There's a 15% chance this could have happened without any change to the signs anyway, under the null hypothesis. So it's definitely not significant. So we'll accept H0, that lambda is still 6, and we will therefore reject H1. So that means there is no evidence, and try and get into the habit of writing the sentence at the end, there is no evidence at the 5% significance level the new signage, I like the word signage, I'll write signs if you like, the new signs have reduced the accident rate.
This is not a bad example, but you wouldn't really do more tests. So continually free and
6 per month.
Yes.
Every time in 6 months.
Yeah, but looking at that, really,
With Poisson, it's going to be independent in different months, you're getting more accidents, like with Poisson.
Yeah, there could be. Yeah, I mean, this is quite limited here because of the numbers. I agree. Okay.
These questions we have aren't really that good.
they succeeded somehow.
At A level, you are given problems which are made simple and non-problematic, certainly to a certain extent, and a lot of the real life problems that you actually would come across are removed from the scenarios. If you go to university, that's when you start dealing with more complicated things, and the most complicated thing is real life to a certain extent, yes, and what actually happens. So we've said here, okay, at the 5% level, no significance. But let's just pose the next question, like a follow-on question here, and to say, what rate of observed accidents in this next month would we have had to have seen to conclude that the signs did make a difference? So the sort of follow-on question here is, how many, or should we say how few might be a better word there, how few accidents in the next month would have suggested the signs worked? It's not the best sentence, but I think we know what's going on. Basically, how many accidents would have had to have fallen to convince us at the 5% significance level? So, how should we go about answering that question? Yeah?
Probabilities that are less than some critical value, and then so they
Pretty much, yes. We will look at probabilities. So we go back to your tables is the easiest thing to do. Look at your tables for lambda equals 6. And look here. We want something, well, we want the biggest number which is below our significance level. What is the biggest probability here smaller than 5%? It's that one there. Yes. So if we sort of do an extract from the tables, we've got when x is 1, the probability is, find the right one, 0.0174. When x is 2, the probability was 0.0620, and these are less than or equal to, so I really ought to put there. Our 5% level is here, between those two, so we would only have rejected H0 at the 5% level if there had been one or fewer accidents. So the answer to that question is one or fewer accidents. And we looked there, I'll write it down in case anybody wants it for the notes or completeness. What we did is we looked for the largest probability that was less than our significance level, and then the x value associated with that probability, that was what sorted that out for us. That's the end of the examples for discrete hypothesis testing. So we've now finished chapter 6 in the book. You've got an exercise 6a, you've got another exercise 6b, you've got 6c. The main thing is the miscellaneous, and you need to realise what's going on here. Miscellaneous exercise 6 actually covers chapter 5 and chapter 6. Part A covers just chapter 5, and part B covers hypothesis testing, which could be discrete or continuous. It doesn't sort of flag it up for you.
How many questions are there?
There are just 22, and it looks like you're suggesting that we do all of them, which is absolutely great. So you actually find there aren't many on discrete that are real OCR questions. In fact, I think there's possibly only one. So do make sure that for the discrete you do more than just the OCR questions only, otherwise you only do that one there. Okay? So work through what you can from chapter 6, but bear in mind that when you come to miscellaneous, when you come on to part B, it's not just chapter 6 that's being assessed, it's chapter 6 and chapter 5 as well. And for Chelsea's benefit as well, we have said there's a homework on the website, on the KRP, for this chapter due on Thursday the 29th, and a test date for this chapter on Tuesday the 10th. Whole chapter 6, just chapter 6.